Hi students, now we are going to discuss the spring mass pulley system by taking another example number 2. So here is the pulley. A string is passed over the pulley. One end of the string is fixed at the bottom and the other end of the string is supported by a mass M. Now the pulley is now not directly fixed. It is connected to a spring and that spring is fixed at a rigid support in the ceiling. So let K be the spring constant and M be the mass and T be the tension in the string. So both the arms of the string will have the same tension T and it will be upwards. Now initially this mass, it is at a rest. Okay. Now I am going to pull this down. So it acquires a velocity V. So there is a change in velocity. As a result, it will have an acceleration A in the downward direction. Understand? Cut. So now this acceleration is in the downward direction. I want to get an expression relating this tension on the right side of the string and the acceleration. So only this portion of the string I will consider. So the tension T must be equal to, okay, T must be equal to this mass M into acceleration A. So I have considered only the right arm of the string where the mass is supported. The tension is equal to M into A. Okay. When I pull this through some distance x in the downward direction, the mass is coming down through some distance x. At the same time, what will happen to the pulley? The pulley is now suspended in support with the spring. So the entire pulley will be stretched down along with the spring. So let us take that the spring is stretched by an elongation x1. So that now the pulley is coming down through the same distance x1. So the left side the displacement will be x1 and the right side the displacement will be another x1. So that the string pulls the pulley through a displacement x1 on both sides. Okay. So there is a relationship between the distance moved by the mass x in the downward direction and the distance moved by the pulley. So here x must be equal to this x1 plus x1. So I will write x is equal to x1 plus x1. So this is equal to 2x1. Therefore x1 must be equal to x divided by 2. Okay, this is required for us in the next coming step. Okay, now you see here on this spring, two tensions are acting, isn't it? Both the tensions are acting at this point. So what is the tension which is acting on the spring is T plus T is equal to what? 2T. And this force 2T must be equal to minus of K times the displacement x1 produced in the spring. So from this equation T is now equal to minus K by 2 into x1. But already what is x1 in terms of x? It is x by 2. So I am going to substitute here x by 2. So this is equal to minus of K by 2 into x by 2. Therefore now we get another equation for the tension T in terms of displacement x1. This is equal to minus K by 4 into x. Okay. So this is equation 2. So now equation 1 is tension T is equal to M into A in terms of the mass. Then the same tension is also equal to minus K by 4 times x. Okay, in terms of the spring constant. Now I am going to equate these two. So M into A is equal to minus K by 4 into x. Therefore, what is the acceleration? A is equal to minus K divided by 4M into x. So this is equation 3. But from the definition of SHM, okay, from SHM definition, A is also equal to minus omega square into x. This is equation 4. So equation 4 is arrived from the definition of simple harmonic motion. Now equating 3 and 4, minus omega square into x is equal to minus k by 4m into x. So cancelling x and minus, now omega square is equal to k divided by 4m. Therefore omega is now equal to root k by 4m. Root k by 4m, and this is equation 5. Therefore what is the period? Period of oscillation is equal to 2 pi by omega. So this is equal to 2 pi divided by root k by 4m. Root k by 4m. Or t is now equal to 2 pi into square root of 4m by k. 4m divided by k. So this is the expression which is required. Okay. Therefore, what is the frequency of oscillation is equal to 1 by period. So this is 1 by 2 pi into square root of k divided by 4m. So this is another equation. Now same equation I am going to verify in terms of law of conservation of energy. So from the conservation of energy, total energy is equal to potential energy plus kinetic energy. So the potential energy of the system plus kinetic energy of the system. So potential energy is stored in the spring, kinetic energy is stored in the movement of the mass. So the potential energy of the spring is minus half k into x1 square. Or only the magnitude I will take. Only the magnitude I will take. It is half k x square. No, in place of x you have to substitute x1. So that is the elongation of the spring. So the potential energy of the spring is half k x1 square plus kinetic energy of the mass is half m v square. Now total energy is expressed in terms of displacement x1 of the spring. Now I want to express this in terms of the displacement of the mass, that is x. So what is x1 is equal to x by 2. So this is now equal to k by 2 into x by 2 the whole square plus m by 2 into v square. Okay. So this is now equal to k by 4 or k by 2 into x square by 4 I will write plus m by 2 into v square. So this is equal to k by 8 into x square plus m by 2 into v square. This is the total energy of the spring mass system. I am going to differentiate this left hand side and the right hand side with respect to time, so that then now left hand side is dE by dt. This is equal to k by 8 is a constant into x square. If you differentiate, it will become 2x into dx by dt plus m by 2 is a constant into differentiating this v square will become 2v into dv by dt. Okay. So this 2 and 2 get cancelled. This 2 and 8 if you divide, it will become 4 2s are 8. So left hand side is dE by dt is equal to 0 because energy doesn't change. Total energy doesn't change. Okay. It is 0. So this is now equal to k by 4 into x. So this is k by 4 into x into dx by dt is equal to the velocity v plus m into v. Okay, m into v into dv by dt is equal to what? Rate of change of velocity is the acceleration. So this is equal to a. So shifting this on the left hand side, m into v into a is equal to minus k by 4 x into v. So cancelling this v and v, a is equal to minus k by 4m into x. Also a is equal to minus omega square into x. So if you compare again, the same step is repeated, isn't it? So if you compare means we can find that the time period is now equal to 2 pi into square root of 4m divided by k. Okay, so already what we have derived by analytical method, we are once again verifying in terms of the law of conservation of energy. So this is The expression for the period of oscillation of such a spring mass system is T equal to 2 pi into square root of 4m by k. I hope you must have understood well. Fine.